Hey guys, welcome to another video of quantum field theory. In today's video, we'll be quantizing gauge fields. So we learned about two main gauge fields. There's mass gauge fields and there are massless gauge fields. Let's start our discussion with mass gauge fields. So mass gauge fields have a Lagrangian with a mass term. And as usual, we can quantize our main field, which is the EM potential, in a pretty straightforward manner. So when we quantize our field with the canonical method, what we do is take our main field of interest, that being the EM vector potential, and we quantize that, or we should really write t and x here, because it's a function on spacetime. And then we want that we want to set up a commutator between that dynamical variable and the momentum conjugate. And we define this relation as being I times delta of x minus x prime. So the conjugate density, to remind you guys, is defined as the partial derivative of the Lagrangian with respect to the time derivative of our potential. And to clarify some things, the EM vector potential, it's a 4-component 4 vector. So we have one A0 component and one A1 component and so on. So we are really defining a commutation relation for each component. So we have one for A1 Tx and then pi1 Tx, and that's going to be I delta x minus x prime. We have another one for the case where mu equals 2. So we have pi2 Tx prime. That's going to be I delta x minus x prime, and so on. So we have a relation for each component of our 4 vector. Now let's actually calculate the commutator explicitly for the first component. So we have that pi mu, the conjugate momentum density, is partial L over partial naught A mu. This means that pi naught is going to be partial L over partial A, or partial naught A naught. Let's take a look at our Lagrangian for the Proctor equation. It's this over here, right? And here is our Faraday tensor explicitly. So we have that F naught naught. So the first component, the time entry of the Faraday tensor, it's going to be partial naught A naught minus partial naught A naught, which gives us 0. In fact, for each entry along the diagonal, the Faraday tensor admits zeros, and then it's non-zero everywhere else. So we can use that structure to deduce that this term is going to be equal to 0, because we have partial naught A naught, right? There's not going to be any partial naught A naught term in our Lagrangian, because the F naught naught term is just going to vanish, where we could have a possible partial naught A naught. That's just going to go to 0. So because of that, this conjugate momentum density is also going to be 0. So if that's the case, that would mean that A naught Tx conjugated or with A naught Tx prime, it tells us that this should actually just give us 0, because this is going to be 0, and anything that's commuting with 0, or the commutator between anything with null, nothing, should give us 0, because that's just A times 0 minus 0 times A, which is just 0. So this should be 0. But we just said before that it's going to be the delta function, right? And that's a problem, because that implies that the delta function, x minus x prime, is equal to 0. But that's a contradiction, because the delta function is a distribution that peaks at x equals x prime and is 0 everywhere else. If it was truly 0, there would be no peak at all. So we have a contradiction here, which is, of course, a big problem. So really, we shouldn't be defining a commutation relation with A naught, because if we use A naught, we get a contradiction. So we should really define the relations only for the cases where mu equals 1, 2, and 3, and leave out the case where mu equals 0. This is telling us that we should really just say that we have a commutator between a I t x with pi I t x prime, and that's going to be I delta x minus x prime, where here this I is not the square root of negative 1. I is just some variable that runs from 1 to 3. Now there is a final small thing that we can add to our relation over here. We can change this index to a j over here, and then under chronicle delta ij. The reason why we're doing this is for this to actually yield out a matrix instead of just a pure delta peak function. Because this chronicle delta, these are entries of a matrix. It tells us the same thing as before pretty much, because delta ij is defined as 1 if I equals j and 0 if I does not equal to j. So for practical purposes, I here is still equal to this j right over here. So here we have written out the EM field for like a mass field. We have to sum over the 3 polarizations. We have the same things as before. Like we saw before, A of k is going to destroy particles. A conjugate k is going to create particles. Here's an example. It can be confusing knowing the role of this E over here. That's just telling us the polarization state. So for E1, we could have this state over here. It represents an EM wave polarized in the x direction. For E2, we can have an EM wave polarized in the y direction. So that's what this S is supposed to represent. Here is S equals 1. Here would be S equals 2. So A1 of k will destroy a particle that's polarized in this state. So now we can dive into the discussion for massless gauge fields, which can describe the photon. So for the photon, it has no mass, so we see no mass term in the Lagrangian. Now we can also work with what's called the temporal gauge. You choose a gauge such that the A naught component equals 0. Now why are we doing this? Well, we saw that before for mass gauge fields, that we don't want the A naught component to play an actual role in our analysis because it leads to contradictions. It shouldn't play a physical role. So you can choose a temporal gauge to make the same exact statement. We can choose a gauge such that A naught equals 0. Now the question is, does this gauge exist? Well, yes, because remember that for massless gauge fields, you can substitute A for A mu prime, where A mu prime is just the original gauge field plus partial mu f of x mu. This means that we are looking for A naught of x mu to be replaced with A prime naught x mu, which is equal to A naught x mu plus partial naught f x mu, which will equal 0, implying that we want A naught x mu equals negative partial naught f x mu. So basically, if there exists some function that satisfies this property right over here, that means that we can choose a gauge such that A naught equals 0. And yes, there will exist some function. Can we prove that? Sure, we could, but that would take us too astray. So, by just noting that we can do that, let's use the temporal gauge. Now recall that the Coulomb condition stated that this over here, and that's just going to be partial naught A naught minus partial I equals 0. So since this is going to be 0 in the temporal gauge also implies that partial I is also going to be 0. So we can call the gauge that A naught equals partial A or partial I equals 0. We can call that altogether the radiation gauge. That's just some terminology that you guys might see in your textbooks. So, knowing this facts, we can now get to work. So what are the implications of using the radiation gauge? Well, the radiation gauge implies that E naught is going to be equal to 0. And this means that 0 is going to be equal to Ki EI due to this relation that we found over here, which was derived from the fact that partial rho A rho is going to be equal to 0. Now, we can let our field be traveling in the purely z direction for some demonstration that's going to follow. And we cannot look in the rest frame for the field because we cannot Lorentz transform a massless field to the rest frame. So before we did that for the product equation, now since we have a massless field, we can't just set the 3 momentum to be 0. We have to work with a non-zero 3 momenta. So we're going to look at the field traveling in the z direction for now, which is what this over here represents. So if we have that, using this relation that we found over here, that would imply that 0 equals K3E3. Because recall that if 0 equals KIEI, that means that 0 equals K1E1 plus K2E2 plus K3E3. Since we are working where the z direction is like the direction of the momenta, that means that these are all going to be 0, meaning that we have 0 equals K3E3. Since like we define K3 to be non-zero, this would mean that E3 was going to be 0. If we did have that K3 was 0, we would just have 0 equals 0, which would be a truism, right? Which kind of hints to us that we can't really Lorentz transform a massless gauge field to the rest frame. So this is telling us that E naught and E3 equals 0. However, E1 and E2 is not necessarily 0. It's not constrained, which means that we have 2 independent polarization vectors. So these are just an example of 2 polarization vectors that we can choose, and these vectors are orthonormal to each other. So an important thing to note that if we can write a general theorem here, like a general theorem that if our field, the EM field, travels in the Ki direction for some value of I, in the Ki direction, this means that EI is going to be 0. So if it travels in the K2 direction, then E2 is 0. If it travels in the K1 direction, then E1 is 0, basically. And that follows from this right over here. So let's look at if the field travels in the Y direction. We already know what's going to be the answer, but let's just check it to make sure. So if you do that, we'd have that 0 equals K2E2, which implies that A2 is going to be equal to 0, because A2 is just E2 e to the minus I k mu x mu. So E2 is also going to be 0. So we can choose, again, these 2 new vectors for the case where E naught and E2 are 0. So the direction of the EM wave changes which components of A rho are going to be 0. Because if you let the field move in the purely z direction, we found that, well, that would mean that A3 is going to be 0. If you let it move in the purely y direction, that would mean that A2 is 0. So this gives us a bit of a problem, right? Because remember that from all the way before, if we had one of these guys being 0, that would lead to a contradiction. So we have to sort of fix this problem somehow. And these are the complications of working in the radiation gauge, but there is actually a solution to this problem. So what we want to do is we want to isolate the relevant vector components for a given 4 momentum, or really just 3 momentum. For example, if our momentum is traveling in the x direction, we do not want to write down our commutator relations that contain A1. So how can we do this? Well, we can do this by using what's called the projection operator. So here, this Pij, this is the projection operator. And it turns out that when Pij acts on J, and that acts on some momenta, J, that's going to give us 0. Which means that this is going to give us some new sort of component. We can call that AI with some little bar on top. And then this is actually going to be Ki. So AI, Ki is going to be 0. So this operator is going to turn our field into a vector that is going to be orthogonal to the relevant 3 momentum, if that makes sense. And we'll do this in practice to sort of make the concept make more sense. So if we were to do that, that would just give us the same thing, but now we are multiplying this by Aj and Ki. Just to clarify, there is no sum going on here. Since downstairs indices are both downstairs, we're not summing over I and J. That's not happening here. So just to clarify that. So to solve this, we have to distribute in the vector. So that gives us delta ij ki minus ki kj ki over pretty much km squared. Now these are going to cross cancel since they're always going to be the same. That leaves us with the kj. For this is only going to be non-zero for when we have kj. So we have an aj over here. So we have kj minus kj aj, and this is going to be 0. So this shows us that this is going to be equal to 0. So we can define Pij acting on Aj. Let's use a new color here. Pij acting on Aj. We're going to define that as being Ai. And we're going to call that the transverse 4 or 3 potential. So by using this concept of projecting things, we can actually now write down our commutation of relations consistently as being AI, transverse delta ij. So if you transverse delta ij, that's going to be simply defined as being the projection operator, which is this, ki, kj, over km, acting on delta of x minus x prime. Okay, so how does this solve our problem? Well, let's actually consider specific cases. So say we have the 3 momenta is going to be 0, ky, 0. This implies that A2 is going to be 0. So we do not want to consider the commutator for A2. So let's actually look at what we get when we do consider the commutator. That'll just be the transverse A2 tx pi 2 tx prime. That's going to be equal to I times the delta transverse of ij, which is just going to be 2, 2. So the transverse delta 2, 2 is just delta 2, 2 minus k2, k2 over km, km, delta of x minus x prime. So if we had that k2 was not 0, or if we had the k2 was 0, right? Say we had the k2 was 0, so the field was not traveling in the y direction purely. That would mean that this over here would go to 0, and this over here would go to 1 since k2 would be 0, right? And that would just give us that the transverse delta of 2, 2 equals our normal delta function, right? But since we do have it that k2 is non-zero, right, that would mean that this over here would become 1, since we would have K2 over K2 over Km, which will like only be non-zero for the case where m does equal to 2. So that would be 1. This is going to be 1 by definition. So this would just be 0. And since that is 0, that's telling us that this over here is going to be 0. And, oops, sorry, I should be looking at the one below that. That will tell us that this over here is 0. And since this is going to be 0 pretty much, we have a true relation where 0 equals 0, which makes sense. We don't have a contradiction anymore. So that's how this sort of solves our problem by using the transverse delta and the transverse field. And to clarify, right, like if we were to consider like A2 is 0, right, that would mean that we have P2 or P1 to A2 equals A this I. Now, and since A2 is going to be 0, and we're multiplying that by some number, we're going to get 0 for this one as well. So that's how this really solves our problem, by using the transverse delta and the transverse EM field. So here again we have our full solution for the EM field, the massless one. Here we can see that we are using the transverse EM field, because that's what we use in our relations. We can see that our polarizations go to 2 this time. And the same thing is pretty much happens. This is going to be annihilation, and you guys already know what this is going to be. So yeah, so that's pretty much it for today's video. From what we've covered in our series so far, we have now mastered the scalar field, Gage fields, and the spinor fields. These 3 fields describe every particle in the standard model. So with this knowledge, we can like do a lot of quantum field theory already. And we talked about the free fields for each one of these cases. So in our next video, we're going to talk about an important effect. It's a very fun effect called the Unruh effect. Now, there are series we've been using Minkowski spacetime, but in the Unruh effect, we consider the spacetime for an accelerating observer. And in fact, for the accelerating observer, they actually see an event horizon behind them. And this horizon is going to produce horizon radiation, which is very similar to Hawking radiation. So we'll be looking at that effect more in detail in the next video. So with that being said, thanks for watching and have a great day. Bye.